Lesson 1.6, electron arrangements. So the idea of this is to be able to write out the electron configuration of atoms up to atomic number 36, so 36 protons, which means it's got 36 electrons, by using SPD notation. Now, if you've completed the dot and cross diagram for calcium, you would put 2 electrons on the first shell, then 8 in the next shell, then 8 on the next shell, and then 2 on that fourth shell, and that's as far as we tell you to go at GCSE. The reason we go no further is because we weren't quite telling you the whole truth at GCSE. The electron shells, or electron energy levels as we call them at A level, are in fact divided into sub-shells or sub-energy levels. And what we want to be able to do is to write out the SPD electron configuration of calcium as shown here on the right, where we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we stop at GCSE. So let's explain what is happening there. Okay, so if we look at the diagram on the left, yours would probably look something similar to this. So calcium has got 2 electrons in the first shell, then 8 in the second shell, 8 in the third shell, and then the final 2 go in the fourth shell. And then at GCSE we tell you to stop there. Now if you look at, let's say, the second shell, what most of you have probably done, and this diagram here, it shows the electrons paired up. Now why do we pair them up? Now quite often many of you will suggest that it's because it looks neater, and yes it does. But in fact why we tend to pair them up is that these shells are not complete shells. They're in fact broken down into sub-shells. Now at A level we call these sub-energy level. Now these sub-energy levels contain themselves orbitals. And an orbital in chemistry is a region of space in which the electrons are probably going to be found. Normally we give the area as a 95% probability of finding the electrons. Each of these orbitals will take a maximum of 2 electrons. Now if we look at the diagram on the left, for the first shell, or energy level as we call it at A level, it is in fact broken down into just a 1s sublevel, or we can call it a subshell. Now this is spherical, so you can imagine a 3-dimensional ball, and for that first shell, and just has this spherical sublevel, or 1s sublevel, in which 2 electrons can exist, and it will only take a maximum of 2 because that sublevel only has 1 orbital. Now it gets more interesting when we go to the second shell, or energy level as we call it at A level. Now in the second shell there are 2 sublevels. Okay, there is a 2s sublevel, and just like the 1s sublevel, this contains 1 orbital that is spherical in shape, and that 2s is slightly larger than the 1s. And again, because it is just made up of 1 orbital, this sublevel will just take a maximum of 2 electrons. And then in the second shell, or energy level, there is a 2p sublevel. Now the 2p sublevel contains 3 orbitals. And again, if you remember, those 3 orbitals will take a maximum of 2 electrons each. There's one, if we assign an x, y and z axis with the origin at the nucleus, there is a 2p orbital that lies along the z-axis, there is a 2p orbital that lies along the x-axis, and one that lays along the y-axis. And each of these orbitals in that 2p sublevel will take a maximum of 2 electrons. Because there are 3 of them, that gives us 6 electrons in total that we can put into that 2p sublevel. So we have a 2s sublevel with 1 orbital that will take 2 electrons, and a 2p sublevel with 3 orbitals that will each take 2 electrons, which means altogether we have 4 orbitals in our second shell, our second energy level. So altogether we can put a maximum of 8 electrons into that second shell. And that's what we've taught you before at GCSE. Second shell, second energy level, takes a maximum of 8 electrons. At A level, we talk about the second energy level being 4 orbitals. 1 orbital in a 2s sublevel and 3 in the 2p sublevel. So let's go on to the third shell, or third energy level. Now the third energy level, just like the first and the second, again has an S sublevel called the 3s sublevel. And again, that contains 1 orbital that is slightly larger than the 2s, and remember the 2s was larger than the 1s. Okay, we can put 2 electrons in that one. The third energy level, third shell, also has P, just like the second shell, P sublevel that contains 3 orbitals. And in each of those 3 orbitals, we can put 2 electrons. And then we've got another sublevel. And you might be able to see a pattern here. The other sublevel is the 3D sublevel, and that contains 5 orbitals. And each of those orbitals will take a pair of electrons. So we've got another 5 orbitals. That will give us times 2, 10 electrons that we can put in there. 6 from the P, the 3p orbitals, and 2 from the S gives us a maximum number of electrons in the third shell, the third energy level, of 18. So why have we lied to you at GCSE? Why have we told you at GCSE the third energy level, the third shell, only takes 8 electrons? And it's because of what happens when you move to the fourth energy level. Now, if we look at this diagram here, what we see is on the x-axis, your distance from the nucleus. And so the 1s, the smallest sublevel being closest to the nucleus, and then the 2s a bit bigger. The electrons are going to be a bit further out. And then the y-axis here is showing the energy. Now, it's exactly the same principle at A level as it is at GCSE. We always fill up from the lowest energy level first. In this case, we look at sublevels though. So we fill up from the lowest sub-energy level first. And if we plot our orbitals on this graph, what we see is that the 1s sublevel is lowest in energy, and we represent here each orbital as a square box. Okay, and the 1s orbital sublevel, is lowest in energy, it contains 1 orbital. Then the next highest in energy is the 2s, which belongs to the second shell, second energy level. The 2s sublevel is next in energy. Then you've got the 2p sublevel, and this has 3 orbitals. Now we represent that by showing 3 boxes, like we've done here. Then you've got the 3s, that's next highest in energy. Then you've got the 3p sub-energy level, which has got 3 orbitals. And then we have, if you look there, the 4s, which is very slightly lower, only very slightly lower in energy than those 3 d orbitals that were from the third shell. So that's why we tell you to stop at GCSE. So we get to the 4s, and then we say go no further, because actually what we need to go back and do is then go and fill up these other, that we didn't know about before, these other sub-energy levels in the 3D. Okay, so if we were doing this for calcium, for example, calcium, we would put 2 electrons into that 1s sublevel. Then we put the next 2 electrons of calcium into the 2s, because that's the next one up in energy. Then we put 6 electrons, and notice how we do it here. Okay, so this is 6 electrons in the 2p sublevel. And what we do here is we occupy orbitals with single electrons initially first, before we start to pair them up. Okay, so if we have more than 1 orbital in a sublevel, The electrons will occupy orbitals on their own, and this is because when we pair them up we get some repulsion energy. Okay, so single occupation of the orbitals first, then we pair up the 3p, so that gives us 2 in the 1s, 2 in the 2s. We've now got 6 electrons in the 2p. Next one higher in energy is the 3s, so I then put 2 electrons into the 3s orbital, and we then put 6 electrons into the 3p, again occupying single orbitals with single electrons before we start to pair them up. And then the last 2 electrons of calcium we put into the 4s. Now, to write this down, instead of drawing out these boxes all the time, to write this down in text, when you're writing a document, we use this notation using a superscript number to tell us the number of electrons in each of those sublevels. So if we were doing this calcium one, for example, we would indicate it as 1s2 to tell us there's 2 electrons in the s sublevel, 2s2, 2 electrons in the 2s sublevel, 2p6, 6 electrons in the 2p sublevel, 3s2, 2 electrons in the 3s, 3p6, 6 electrons in the 3p, and then 4s2. Okay, so we need a way of remembering the order of the sublevels in terms of their energy. And what you can do is to use the periodic table, because the periodic table is increasing by atomic number of 1 each time, which means that the periodic table is increasing by 1 electron as you read it from left to right going across the elements. So for example, hydrogen, our first element on the periodic table, has an atomic number of 1. That means it's got 1 electron. So it would have 1 electron in the 1s sublevel. It would be 1s1. Helium is next. Helium has 2 electrons. And helium, again, those 2 electrons would go into the first 1s sublevel. So it would be 1s2 for its electron configuration. So going across that first period, we've filled up the 1s sublevel. Because the last electron we've put in for both of those was in an s sublevel, we call this an s block element. Now if we go to period 2, let's have a look at lithium. Lithium's got 3 electrons. So it has got 1s2 sublevel completed. So there's 2 electrons in that 1s sublevel. And then it's got 1 electron in the next sublevel, which is the 2s. So it would be 2s1. Again, it's an s block element because the last electron we've put in was in an s sublevel. Then you've got beryllium. Now beryllium would be 1s2, because it's got 4 electrons, 1s2, and then we fill up all of 2s2. Again, it's an s block element. Then if we go across to boron, we've moved into a new sublevel. So we've got 1s2, 2s2, and then 2p1. We've put 1 electron into the 2p sublevel. And you can see what that takes us into now is the p block. And it's in the p block because that last electron we put in was in a p sublevel. Next one, carbon, would be 1s2, 2s2, 2p2. So we can read the periodic table a bit like a book. So going from left to right, and by knowing the sublevel that that block refers to, we can work out quite easily the ordering of those energy levels. Now, the only time you have to be careful is when you get to scandium. Now, if we look at scandium, we'll start from left to right again at the top. So scandium is down there at the start of the D block. And what we need to remember is that those D sublevels, the in that third energy level, we're lower in energy than the 4s. So we were filling up the 4s first, because this 4s sublevel is lower in energy than the 3d. So if we work on scandium, scandium is 1s2, 2s2, 2p6, 3s2, still going, 3p6, 4s2, and then the next one is a 3d sublevel. So it's 3d1. And so this scandium is a D block element. Okay, have a go at the rest of the elements in the task. There are a few ions on the sheet, just as an extra bit of challenge, and then a research task. Can you have a look at chromium and copper and see if you can work out the electron configuration of those?